Thanks, Maxim. And hi, guys. Kevin here with Infer. I'm going to go ahead and start to maybe share a bit of a presentation. And Maxim, that was pretty good in terms of an overview. I appreciate that. So Infer, we call ourselves a secret computing company. Really what that means is privacy preserving machine learning and analytics, and a bit about what we'll tell you today. And I think the vector of application is really just machine learning and AI are here. What's often holding it back is issues around plain old access to the data, with a quote from some friends at Google's TensorFlow. And really, as a result of frictions, we're facing privacy issues, explainability issues around accessing this data or using data compliantly within the proper context that today is resulting in headwinds, whether we call that data silos or bias developing in AI or friction around data sovereignty, compliance, and even monetization of data. It's really the reasoning why we built Infer and focus on bringing cryptography into the application of data analytics. And just to set a bit of the stage, what we talk about Infer in terms of secret computing is really a third pillar of encryption, where classically you might be familiar with encryption in transit. So here we are on Zoom, and perhaps these communications are encrypted, I think, with Zoom these days, along with encryption at rest. You know, when you AES encrypt a file, kind of what Jim and Steve were talking about. At Infer, we're focused on the more elusive target of operating on data in its encrypted state. We call this secret computing. And it's a bit more complicated given the need to manipulate data while encrypted, but it affords us interesting privacy and utility trade-offs that are very, very applicable in terms of the advanced analytics space. And so it's not just about protecting your data, but it's actually about what you can do when you can also check the box on compliance and privacy of your data. And the way that we deploy that and our customers utilize it at Infer is augmenting and developing more precise, more accurate, or more explainable predictive models
Kevin?
Through the use of broader and deeper data pools.
Kevin,
yes,
I also want to mention I believe if you have a slide presentation, you're not sharing the screen yet.
I'm not sharing the screen. Maxim, I'm sorry. I thought you might have been kicking it over to me. Let me take it. How about now?
Yep, seeing it now.
Cool. So just quick recap. Secret computing for us, really, it's privacy preserving machine learning, bringing privacy into the mix of data and analytics that allow us to move past some of the friction points we see around data sovereignty, bias in AI, data silos that inhibit some of the data analytics that are possible and capable today. The way that we do that is with in-use encryption. So this is the third pillar of encryption. It's in contrast to encryption in transit or encryption at rest. It's the more elusive scenario that we focus on deploying. And the way that we do that is through three primary applications that we talk about: intra-organizational, inter-institutional, and more ecosystem development that allows users to build more accurate models, whether you look at that from an AUC perspective or other precision and accuracy metrics. What we're really looking to do is bring cryptography and mathematical guarantees to data privacy, data security, and data localization to satiate our advanced analytics desire to consume more and more diverse or deeper data sets. And we're really just scratching the surface across these use cases, largely in the financial services space, helping institutions develop cross-border or cross-boundary machine learning models that comply with GDPR requirements, along with interesting intersections within the capital markets space, developing risk models and trading models, preserving underlying data privacy, and really interesting expansions in more of the pre-competitive ecosystem development, particularly around fraud and anti-money laundering, where data privacy for large financial institutions is paramount, but there's great utility in more precise models to accurately sort or classify good and bad transactions within largely unbalanced data sets. To kind of put this a bit in perspective across some of the other privacy enhanced technologies or techniques that most might be familiar with, really we're using cryptography to move us past trade-offs that often exist between privacy and precision, where we might have brought things like anonymization, pseudo-anonymization, or de-identification protocols. There's also mathematical noise that can be injected into analytics around differential privacy, or even hardware-based solutions from enclaves and trusted execution environments. Where we focus actually is more using tools like fully homomorphic encryption and secure multi-party computation that move us past this trade-off, largely though at the trade-off of incremental compute, with really this premise that you can kind of have your cake and eat it too, but you bring more computational power to the mix. And in doing so, we kind of support that with the thesis of, as compute and cloud comes online, what have we largely done with it over time? We've done more precise, more performant, and more big data. And it's about time, given geopolitical, political, and personal rhetoric, that we start to allocate some of this compute to doing so privately. So doing all of the fun analytics that we're talking about, but also satiating the privacy and compliance reasons with that data behind it. And so just to take a step back and kind of introduce how this happens, one of the underlying technologies I mentioned is secure multi-party computation, which really allows us to kind of tackle a problem like this. Party A has data and party B has data. And we'd like the utility of analyzing that data as if it was aggregated or conjoined together, but we can't do that for one reason or another. We also don't want to centralize that information into a third party or a honeypot that might also represent even greater compliance or privacy risks. So to do that, we're going to kind of unpack a really introductory premise called the Yau's Millionaire problem in privacy preserving multi-party computation, where we want to do a simple function of summing the salary of 3 individuals, but do so privately. We kind of set that up by distributing and deploying infrastructure that allows us to encrypt the data and then compute on it. So essentially what we do is we tell Ali, Brian, and Caroline in this scenario to encrypt their data into correlated secret shares. And we've got a massively simplified example, but Ali might encrypt her data, keep 1 share for herself and distribute it to others. Brian and Caroline both do the same. Each player then left with what's called a secret share or an encrypted version of the underlying data. And then we ask them to perform a local operation where they sum their encrypted versions of the data and broadcast back a result, which allows us to have the equivalent and a very precise equivalent of the plain text computation, all while injecting a privacy preserving protocol. Now, very massively simplified example that gets much more complex when you start wanting to do gradient descent or logistic regression processes, but a good summary of how this principle works in one of the underlying technologies. To kind of bring it into how we deploy it to our customers at Inpher, it's a software as a service product or just a SaaS-based component that has 3 primary access points. One being an analyst portal, which is able to be interacted from a few different methods, whether it be an API, a Python language, or a UI, which we often show and demonstrate, as well as an XOR service, which is a cloud-hosted service often talked about as this trusted dealer in a privacy-preserving computation, along with a number of virtual machines, which are deployed in the privacy zone of the data set in question. And so there is no lift or shift. We're essentially bringing compute to the data versus moving data to the compute, which allows us to really check the boxes on some of those privacy requirements. And so the way that someone might utilize it and operate with this is that an analyst submits a function, f of x, sum, divide, compare, train a logistic regression model, or execute forward propagation and inference to the XOR service, which compiles a circuit and generates random triplets to create a cryptographic protocol, which are then distributed to the players, to the virtual machines within the data source zone's privacy set, and allows them to then begin an online multi-party computation, as seen in the earlier slide, to broadcast back their partial result, which gives us precision today up to and beyond 8 digits after the decimal point. So really where we focus on in deploying XOR is high precision, privacy preserving analytics that are often focused on significantly unbalanced data sets that need more and more diverse or deep depth in the data that they train on. And so the way that someone might operate and interact with this can be our REST-based API, the GUI, which if there's interest in the group here today, we'd love to find time to show and highlight some exemplary use cases, along with some of more of our end users using a domain-specific language or a Zorpi Python extension to really just interact with this as they might from their workstation or things like their Jupyter notebook today. To get a sense of really where we operate and deploy this, we spend a lot of time in financial services. I would say healthcare is a rapidly expanding area where things like patient selection or clinical trials or even advanced diagnosis are gaining incremental insights from training or analyzing more diverse data sets. Additionally, this is hopefully something that maybe is coming onto your radar. We'd be happy to point to some of the really interesting third-party pieces that are talking about privacy-preserving computations and secret computing, from the likes of Gartner to the World Economic Forum. But more importantly, we'd love to kind of map some of the exemplary use cases that we're working on and our clients have deployed today to the cohort of plug-and-play sponsors and corporates that have interest in developing more precise predictive analytics while also satiating compliancy reasons. And just a bit on the company, a little bit of our background and where we're based. We're a Swiss-US company headquartered in New York. I'm coming to you today from sunny California, and a large team in Lausanne, Switzerland. A bit, as Maxim mentioned, we have raised our Series A from some of the classic California VCs along with JP Morgan. And we'd be happy to talk more about any of these scenario or any of the stuff we've shared today, but more specifically, how it might map into your business. And maybe Maxim, with that, I can kick it back to you for any Q&A.
Amazing. So first of all, in the audience, if you like an introduction to Infer, please indicate in the poll. We have a couple questions from the audience. So first off, how do you differ from other encryption solutions such as Duality technologies?
Yeah, good question. So Duality focuses on leveraging a singular fully homomorphic encryption capability, which is one of the underlying cryptographic protocols that we also utilize at Infer. We have one of the fastest fully homomorphic open source toolkits on the market that we develop and support called TFHE. I'd encourage you to check out TFHE and Chimera and some of our open source fully homomorphic encryption tools out there on GitHub. But more importantly, we focus our efforts on a broader set of privacy preserving techniques that include fully homomorphic encryption, as well as other things like multi-party computation, garbled circuits, private set intersections, and a more diverse set of cryptographic techniques that we call secret computing capabilities. The same way you might talk about data science being an umbrella term for a number of different predictive analytics capabilities like regression and neural networks and boosting and others. And so that's a bit about how we compare and contrast that, but we all do operate in the privacy enhanced technology space.
Got it. And then second question, are there scenarios where data can't be analyzed while it's encrypted?
Great question. Maybe where that's coming from, you can reach out through Plug and Play and we can have a deeper discussion about what that scenario might be and determine whether it fits or not. But I think in terms of known limitations of cryptographic protocols for analytics today, we're not really talking about massively big data sets in the terabytes and petaflops of the world because of the incremental computational power that's required. So data sizes and analytics are, kind of one dimensionality of where we look at understanding what technique properly fits that scenario and that privacy preserving mean. And we build that through a compiler based protocol that allows us to chain multiple operations to kind of tackle a range of different scenarios. So I would say probably the largest limitation that we've seen today is people wanting to really crunch terabytes of information in near real time, and we're just not yet at that performance scale, though there are massive improvements that we continue to make in the performance and the scalability of the platform.
Got it. Appreciate it. Thanks, Kevin. And if anybody has additional questions, please, indicate and feel free to reach out to Kevin afterwards as well.
Right on. Thanks, Maxim.